So now we're going to talk about transformations a little more generally. And to do this, we're going to use some notation. So we're going to use this uppercase T to refer to the transformation. And we're going to use uppercase Y and X to refer to the codomain and the domain. So this is a transformation between sets. And if we're talking about elements in that set, we're going to use something really similar to function notation. T parenthesis x equals y. So this is between elements of the set. All right, so let's introduce a definition regarding a general transformation. So we have this general transformation that goes between sets and it takes elements to elements, and we say that this transformation is linear if it satisfies these two conditions. And the first condition is that if you have a constant times x, then that's the same as the constant times the transformation of x. And then in a similar fashion, if you have a sum and you transform that sum, then that's going to be the sum of the transformations. So here's the first example. We want to show that a transformation that's defined by this matrix multiplication is a linear transformation. So we're going to go through the two properties that make a transformation linear. We're going to show that both these properties hold for this matrix transformation. So the first property is if we take c times x and we transform that, that's going to be c times the transformation of x. So let's put c times x into this formula. We're going to multiply a by c times x. And just using properties of the matrix vector product, we can see that that c can move to the other side. And this is just t of x, so we'll have c times t of x. So it satisfies the first property, that the constant moves out, and you can see that it's happening because that's a fact about matrix vector products. And the second property is if we have two vectors, x and w, and we sum them and we transform that, then that is going to be the transformation of each of them added together. And we can see that that holds when we do matrix vector products because the matrix distributes. And we get the transformation of x plus the transformation of w. So this is indeed a linear transformation. So second example, I'm going to show that this transformation, taking a vector in R2 to another vector in R2, is not a linear transformation. So to show something is not a linear transformation, we just have to show that one of these two properties does not hold. So we'll just consider the first property. Let's consider 1. So we're going to look at the transformation of c times x. Now x is in the form x1, x2. It's given as components, so we'll maintain that description. Just using what constants do to vectors, we're going to scale each component. And then we're going to use the formula. So the formula says the first component of this vector goes down here, and the second component goes up here. It doesn't matter that it's a c, the c just comes along for the ride because that's what the formula tells us to do. And this is reminiscent of what we do with functions. If we put something odd into a function, it's not anything crazy. We're just putting that odd thing wherever the function tells it to go. So we're putting cx1 down here, so that's what the function tells us to do, and then cx2 goes up here. And now you see that there's a problem here because we can't factor the c out. There's no way to factor the c. It's not equal to c times 1 plus x2 x1, which is c times the transformation of x1 x2. So these two things don't equal each other. And because of that, it can't be linear because it's not satisfying that condition that those things must be equal. So not all transformations, this is a transformation, but not all transformations are linear. So even though this is a transformation, it has a formula, it's going from one set to another set. It's not a linear transformation. So one last example, we want to show that this transformation, where we replace the 1 with x1, is a linear transformation. So once again, we'll go through the two properties and show that this one satisfies both. So we'll look at t of c times x1, x2. Do the same thing we did before. We'll distribute that scalar into the vector, and then we'll use the formula to put those two pieces in. So the first piece will go here and here. And then we'll notice that this has c in every piece. So it can factor out. That's good because this is going to then be c times the transformation of x1, x2. You see that this is x1 plus x2 over x1, and that is the transformation. So this satisfies the first property. Let's look at the second property. So the second property says if we sum two vectors, and we take the transformation of the sum, that's going to be the sum of the transformations. So we'll add those two vectors so we can apply the formula. This is x1 plus w1, x2 plus w2. Then we'll use the formula, putting those two pieces in their respective locations. So x1 plus w1 is going to go here and down here. And x2 plus w2 is going to go up there. And then if we write this as a sum of two vectors, we can collect all the x stuff in one vector. So this will be x1 plus x2, x1, and w1 plus w2, w1. So we have the w stuff and the x stuff collected in two groups, and then that is the transformation of x1, x2, and the transformation of w1, w2. So it satisfies that second condition, and thus this is a linear transformation. Thus T is a linear transformation.